Welcome back, everyone. This is your boy Kamal once again, and today we're going to be talking about half or fractional derivatives. We're going to see how these exotic little operators are defined, and it turns out it's pretty cool. And we're going to extend our knowledge to other exotic operators like this negative half derivative operator. What does it do? We'll find out later. And along the way, we're going to test all the new knowledge we've uncovered. And by testing everything, I mean see that the results agree with the results we would get from ordinary calculus. And if you're interested in some more background knowledge on fractional calculus or some further exploration, then I've linked a textbook in the description to this video. I highly recommend that, and pretty much the material of this lecture or this video is collected from knowledge within that book. So it's an excellent read, and don't worry about this video. This video is pretty much self-contained in that I'll give you something to start with, and we'll build up from there. So what exactly is my starting point? This is how a fractional derivative is defined. We'll call the operator d the derivative operator with respect to x. And the derivative of order alpha, where alpha lies between 0 and 1, so yeah, fractional derivative it is. So this operator, when applied to a function, in order to apply it to a function, that is, you need to take the reciprocal of gamma 1 minus alpha. You need to multiply that bad boy with the derivative with respect to x, that is, yes, the familiar ordinary derivative operator, of the integral from 0 to x of the function f with the dummy variable being replaced by t, and this whole thing is going to be divided by x minus t raised to the alpha integration with respect to t. See? I told you things were going to get exotic. So this is pretty cool. And let's look at a nice example of this. We're going to be talking about the half derivative. So we have alpha equal to 1/2, meaning that the half derivative of the function f of x is equal to 1 minus gamma 1 minus 1/2 is just gamma 1/2, and gamma 1/2 is famously equal to root pi. We have the derivative with respect to x of the integral from 0 to x of f of t divided by root x minus t dt. Okay, cool. Now let's test this out on a very simple function and then do a thorough analysis of the results. We're going to start with the very simple case study of f of x being equal to x. In this case, we have the half derivative of x being 1 by root pi times the derivative with respect to x of the integral from 0 to x of f of t, so we have t over here, divided by root x minus t dt. Now, the resulting integral is a pretty simple one. All we need is a negative sign here and here, so that we have negative 1 by root pi times derivative with respect to x, integral 0 to x of, now let me add a 0 there. And the special kind of 0 I need is x minus x. We're dividing by root x minus t dt. So on some simplification, we have 1 by root pi, derivative with respect to x, integral 0 to x of root x minus t minus x divided by root x minus t dt. And we're integrating with respect to t, so the x term over here is a constant for this integration anyway. So we have a couple of really easy antiderivatives. We have negative 1 by root pi, derivative with respect to x of what exactly do we get? Here's a power of 1/2, so you should get 2/3 times x minus t to the 3/2 with a negative sign because we have x minus t over there. Then you have a plus sign over here, and yeah, that's 2x root x minus t, and the limits of integration are 0 and x. Now, as t approaches x, we just get zeros. However, as t approaches 0, we get some non-zero terms here. What we have is 2/3 of x to the 3/2 minus, what exactly now? It's 2 x to the 3 halves again. Okay, cool. So what exactly is 2/3 minus 2? That would be negative 4/3, right? So what we have here is 4/3 root pi derivative with respect to x of x to the 3 halves, meaning that all we need to do is apply the power rule. So we have 4/3 root pi times 3 halves of root x, some really nice cancellation. And finally, we have the half derivative of x sorting out to 2 by root pi times root x. Now let's take one moment to appreciate the result. Let's think about it. If you apply the derivative operator to x, what would we get? We would get x to the 1 minus 1, correct? Which is x to the 0, and that is, of course, 1. Here, what's happened is the exponent of x has been reduced by a factor of 1/2, and that's why you got root x. So intuitively, it's making sense for now. But of course, we need one more test to actually prove that this is making sense, that this operator is legit. It's actually working out and giving results that aren't contradictory with the existing body of calculus knowledge, right? That sounded cool when I said it. I don't know why I said it, but it sounded extremely cool. Anyway, I'm not going to spoil the moment. Here's what I'm thinking. Well, what we're thinking anyway. Let's say we write the derivative of some function f of x in this manner. So the second derivative would be the derivative of the function d f of x. We might as well write this as d square f of x. And in general, we denote the nth order derivative with respect to x as d to the n. That's the derivative operator applied n times. So it would make sense if we extend this to say that the derivative of a function f of x, the derivative operator applied once, could be something like d to the 1/2 plus 1/2 applied to f of x. So we could say that this is the half derivative operator being applied twice. That means if we applied the half derivative operator twice, we just get the result that the ordinary derivative operator would give us. What we're trying to imply here is that if we applied the half derivative operator to the half derivative of x, we should get the derivative of x, which is 1. So let's test that out. So we're interested now in the half derivative of the half derivative of x, and that would be the half derivative of 2 by root pi times root x. Now with the definition of the fractional derivative, we saw those differentiation and integration operators, so the constant here would be treated, well, like an ordinary constant and just taken out. So we have 2 by root pi times the half derivative of root x. That's what we're interested in now. So that means we have 2 by root pi times what exactly? We have 1 by gamma 1 minus 1/2 again, gamma 1/2 times the derivative with respect to x of the integral from 0 to x of f of t. So that would be root t dt divided by root x minus t. Okay, cool. So gamma 1/2 is just root pi again. So now we have 2 by pi times the derivative with respect to x of the integral from 0 to x. And let's expand by root t. So we have t dt divided by root t times root x minus t. And now for a simple u substitution, we're going to let root t equal u, which implies that 1 by 2 root t dt equals du, or 1 by root t equals 2 times du. And the limits of integration now change to 0 to root x. So this implies that the half derivative of 2 by root pi root x equals 2 by pi times the derivative with respect to x of the integral from 0 to root x of, okay, so we have t sorting out to u squared. Then we have dt by root t becoming 2 times du. So that's a factor of 4 now outside, divided by root x minus u squared. Once again, we could use a negative sign for simplification purposes. So we have negative 4 by pi times the derivative with respect to x of the integral from 0 to root x of x minus u squared minus x, where once again we've expanded by 0, divided by root x minus u squared. Now the result is a couple of, again, really simple integrals. We have integral 0 to root x of root x minus u squared minus x divided by root x minus u squared du. Now these are a couple of really standard integrals you can evaluate. I'm just going to present you the results. So we have negative 4 by pi derivative with respect to x of pi x by 4 minus pi x by 2. So that sorts out to negative 4 by pi derivative with respect to x of negative pi x by 4. So there's some nice cancellation taking place. The negative sign goes away, and the derivative with respect to x, the derivative of x with respect to x is, of course, 1. So we do indeed have that the half derivative operator applied twice to the function f of x equals x does yield exactly the same result. Notice that in the midst of our analysis, we've actually uncovered the derivative, the half derivative of root x, that is. And we see that the exponent of root x has been decreased by a factor of 1/2, which is why we don't have any x terms on the right-hand side. Okay, this is looking good so far, but an interesting question arises if you apply the half derivative operator to a constant that could be a real or a complex number. So let's apply the half derivative to some complex number alpha. That would give us, once again, 1 by root pi because of the gamma 1/2 term, derivative with respect to x of integral 0 to x, alpha, which is just a constant, so take it outside, alpha by root pi outside, derivative with respect to x, integral 0 to x of dt divided by root x minus t. Again, a very easy integral to evaluate, and I'll just leave that as a little exercise to you. This integral here actually just sorts out to the reciprocal of root x. So this implies that the derivative, the half derivative of a constant, equals that constant divided by root pi times 1 by root x. And wow, this is surprising. We have a derivative, a kind of derivative of a constant not giving us 0, and that is pretty fascinating. But again, we got to be skeptical here. Can we actually conclude that this thing works? This thing works as it should. We'll apply the half derivative operator to it again and see if we get a 0. So we have derivative of half derivative of alpha, which is half derivative, what am I doing? Which is half derivative of alpha root pi times x to the negative 1/2. And again, we have alpha divided by root pi times the half derivative of x to the negative 1/2. Now let's expand this in the integral form. We have alpha divided by root pi, 1 by root pi again, derivative with respect to x, integral 0 to x, and now the function is t to the negative 1/2, or I could just write this as dt divided by root t times root x minus t. And all you need is one substitution of letting root t equal u, and that would yield half derivative. I keep writing negative half derivative because I want to get to that concept later in the video. Anyway, so we have half derivative of the constant alpha turning out to be alpha divided by root pi, and you definitely need a factor of 2 there as well. Okay, derivative with respect to x what exactly? We have integral 0 to root x, and we have du divided by x minus u squared, which is just one trig substitution away from giving you a result of pi by 2. So this integral here sorts out to pi by 2, which is independent of x. So the ordinary derivative operator would yield a 0, implying that the half derivative of the half derivative of a constant alpha does indeed yield 0 as expected. Also, in the midst of this test, we got another very peculiar result. I mean, this is incredibly strange. We have d to the 1/2, and we know that the derivative, the half derivative of a constant alpha, is that constant divided by root pi times 1 by root x. But wait, if this thing equals 0, and alpha divided by root pi is just a constant, that means the half derivative of x to the negative 1/2 is indeed 0, which seems like an anomaly over here. But again, this is very interesting, and we're just playing around here with the half derivative operator. And let's continue this playful exploration by extending values of the alpha parameter. It's bound between 0 and 1, but what if we could extend it beyond 1 and beyond 0 as well? What if we could define something like d to the 3/2 of a function f of x? Well, given the way we've been constructing differential operators, we might as well write this as d to the 1 plus 1/2 of f of x. In other words, this is the derivative of the half derivative of the function f of x. So again, taking the example of f of x being equal to x, we would have the 3/2 derivative of x equal to the derivative of the half derivative of x, which is 2 by root pi, times root x. So on applying the derivative operator, we would have, what exactly? That would be 1 by root pi times 1 by root x. Okay, cool. And again, we see that intuitive sense of the exponent of x being decreased by a factor of 3/2, because 1 minus 3/2 is negative 1/2. So yeah, that's pretty much what we got. And what if we take this another step further in the reverse direction by extending the values of alpha to values less than 0? And how exactly could we do that? Can we define something like d to the negative 1/2 of f of x? Again, the way we've constructed operators, there is some hope. We have d to the negative 1 plus 1/2 of f of x. Like, whoa, that is d to the negative 1 of the half derivative of the function f of x. What on earth is this thing here? What is d to the negative 1? Well, that would be the inverse operator to the derivative operator. So the inverse operator for the derivative with respect to x would be the integral with respect to x, right? So if we define the negative half derivative in this manner, we have d to the negative 1/2 of our function x being equal to d to the negative 1 times the half derivative of x, which we know and love to be 2 divided by root pi times root x. And because this inverse operator is the integral operator, we have 2 divided by root pi times the integral of root x dx. So on integration, we have 4/3, and this root pi in the denominator times x to the 3/2. Yo, what the? So the half derivative, the negative half derivative operator, is more like a half integral operator. So I'm just going to add a constant of integration over here, given that we do have an indefinite integral. So yeah, this could be thought of as an interesting way to define a half integral of x. So yeah, that is pretty damn cool. Anyway, what if we could introduce these half antiderivatives in a different way given the analysis we've performed so far? Like, for example, I could write the half derivative of x we know that this is equal to 2 by root pi times root x, but if I introduce the concept of half integrals or half antiderivatives, then I would get d to the negative 1/2 of root x being root pi by 2 times x. And is that the case or not? Let's verify this. Let's see if this thing works too. So another test subject that we have is d to the negative 1/2 of root x. That would be d to the negative 1 of d to the 1/2 of root x. And we calculated this before. We know that this thing here equals root pi by 2, correct? So the integral would be root pi by 2 times x. And here we have our half integral being pretty much correct up to a constant of integration. This is, again, extremely cool. Let me know in the comment section if you found any more cool results playing around with these half derivative and fractional derivative and fractional integral operators. I hope you enjoyed the video. I had lots of fun. Be sure to like and subscribe. Do drop me a follow on Instagram and support the channel if you want on Patreon. Thank you. See you next time.